Hi everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's lecture we will study about the Gaussian Process Regression GPR, which is a Bayesian non-parametric approach to machine learning, and it is a very powerful approach because with it you can also make error estimates for the predictions that your model has come up with, and that is a nice feature of a machine learning model. Before we get started with Gaussian process regression though, I want to introduce to you the concept of a non-parametric machine learning model and a parametric machine learning model. So let us go ahead and get started. The first topic for today is the concept of a non-parametric machine learning model. Right, so what does this mean and how does it relate to our study of various machine learning models. So a non-parametric ML model is a model that does not make strong assumptions about the form of the function that is being learned. Okay. So you do not make any strong assumptions about the form of the function that is being learned. So if you look at something like a decision tree, you sort of dynamically figure out the architecture of the tree. So you are not making any strong assumptions, what will be the first feature, second feature and so on. You adapt the tree as and when the training happens. However, in linear regression you have assumed a certain form, right. So there are weights and biases and they combine in a linear way to make your prediction. In a neural network similarly you have again assumed a sort of an architecture, right. There are a certain number of layers, certain number of nodes and so on and so forth, and that is fixed. So those are all parametric models. However, if you look at non-parametric models, and they include kernel models like kernel ridge regression, kernel support vector machine and Gaussian process regression that we will be discussing today. So in those kind of models you do not make any strong assumptions of the type of function that is being learned. So predictions for a new data point typically, right, are made based on how similar the features of the new point are to data points in the training set. Right, in the space of features again. Okay, so this is how a non-parametric machine learning models, right. So essentially you are combining the training set, the training data, and then you are trying to predict the value of the target variable for an unseen data point. So I hope you understood what is the basic concept. Now just let us look at a few example cases. So what are the examples? So some examples are, and I already mentioned a few of these to you, these are decision trees, because you do not assume the architecture of the tree a priori, it comes during training. Then you have kernel based support vector machines, because the kernel function can be arbitrary, you can use any type of kernel. Then k nearest neighbor, and that is a model wherein predictions are based on the nearby points in the data set, and this is something we do not have the time to cover in this course, but it is a widely used model. And you also have Gaussian process regression, which we are going to study today. So these are some of the non-parametric models, and these are opposed to parametric models. Right, such as linear regression, ridge regression, lasso, and so on. As well as neural networks, because you have to assume a certain kind of an architecture. Now kernel ridge regression, however, falls into the non-parametric class, right, because anything with the kernel, right, you are free to choose the kernel, and therefore you do not have to make any strong assumptions about the function being learned, and thus it is more about the similarity of the data point, right, the similarity of the features of the new point with respect to the features of the data points in the training set. So then it becomes a non-parametric machine learning model. So with this understanding at hand, let us go ahead and study Gaussian process regression. This is the last machine learning model before we will delve into the field of deep learning and neural networks. Okay. So what is Gaussian process regression? So GPR, also known as kriging, especially in the field of geostatistics, GPR is known as kriging, is a Bayesian approach to machine learning, and especially to regression problems, right. There is also Gaussian process classification, but we will not study that in this course. So in this approach, the prior distribution of the space of functions right, and these are the functions we are trying to predict, right. So you can think of every machine learning model as a function approximator. This is something we have discussed many times before, and the prior distribution of the space of functions in which this function approximator lies is assumed to be a Gaussian process, GP, and that is where the name Gaussian process regression comes from, right. And after you have assumed it to be a Gaussian process, you then use the observed data, and this observed data is used to determine the posterior distribution of the function being approximated. From where the target variable is predicted. Okay, so you have a prior distribution which is a Gaussian process, and then you use the training data, the observed data, to determine the posterior distribution of the function that you are trying to approximate, and once you know the distribution of the function that is being approximated, you can extract the value of the target variable and you can make predictions. Okay. So, this is the more lengthy description of Gaussian process regression, but if you wanted to write it in short, you can say that GPR is a non-parametric machine learning model. So, already you are bringing in the aspect of the prediction depending on how similar the features of the unknown point are to features of the data points in the training set. So, it is a non-parametric machine learning model wherein predictions are made based on a latent function. The hidden function that is being approximated, which is modeled as a Gaussian process. Okay, so, this is the very short description of Gaussian process regression. So, how does this all work mathematically, right? So, first you assume, right. So, this is the prior assumption that the function you are approximating is a Gaussian process, and a Gaussian process is characterized by a mean and a covariance. Okay. So, a Gaussian process is characterized by a mean and a covariance matrix, and this mean function is essentially the expected value of the function that you are trying to approximate, and then this is the covariance, right. So, this covariance between f of x and f of x dash, right, one data point and another is, as you know, that is the expected value of f x minus the mean of f x times f of x dash minus the mean of x dash. Okay. So, this is the covariance matrix, and this covariance matrix is approximated by a kernel function. So, again, as you see in most of the non-parametric models, just like kernel support vector machine, kernel ridge regression, in GPR also there is a kernel function, right. The difference here is that it is formally being used to model the covariance of the function that we are trying to model as a Gaussian process. Okay. So, now what is this Gaussian process? Can we understand it a little bit more, which will help us in our journey with Gaussian process regression. So, let us formally explain what is a Gaussian process. So, a Gaussian process abbreviated as GP is a stochastic process characterized by a collection of random variables and in our case the collection of random variables is the function, right, at every point at which we want to predict it. So, that is a collection of random variables such that every finite collection, every subset of these random variables is or follows a multivariate normal distribution. So far in this course we have looked at a normal distribution of a single variable, right. However, we have also been introduced to the concept of joint probability density functions, wherein two or more random variables, they are jointly following a certain probability distribution. Okay. So, how does that pan out in this case? Okay. So, in this case you have to let us assume that you have some x, right, that follows a multivariate normal distribution. Then you have to specify a vector of means, and then you have to specify a covariance matrix. Now this x, I am not using it to represent the data matrix here. This is just something, this is just a particular collection of random variables which follows the multivariate normal distribution. Okay. So this mu is the vector of means, and this is the covariance matrix. So you see why the covariance matrix is required in Gaussian process regression, because we are working with a multivariate normal distribution. So in this case, this collection of random variables will follow the joint probability density function based on the features x1, x2 to xp, or the random independent random variables x1, x2 up to xp. This will be given by an exponential minus half x minus mu, right, the vector of means transpose, then the inverse of the covariance matrix times x minus mu vector, okay, divided by square root of 2 pi to the power p determinant of the covariance matrix. Okay. Now this p is essentially the number of random variables in the Gaussian process. Right, we are considering when we write this joint probability density function, and then this sigma here, like we said, is a covariance matrix, but you do see that you have to take a square root of the determinant. So then this is defined when determinant of the covariance matrix is greater than 0. So that means your sigma must be a positive definite matrix, and the concept of positive definiteness we discussed many lectures ago when we were talking about Hessians and how we can ensure a local minimum of a loss function. Now in the unrelated case here of a multivariate Gaussian distribution, the covariance matrix needs to be positive definite. It has to have all positive eigenvalues, because only then the determinant will be positive and you can write this multivariate normal distribution. So that was the discussion about Gaussian process. Now how is this Gaussian process useful to us, right. So now this is where we have to move from the Gaussian process that we have assumed for the function that we want to approximate, and we have to update this prior knowledge, right, in a Bayesian approach. This is the prior knowledge, and we have to update it with the data that we have at hand, right. So now given data x comma y, right. So you have a matrix of data x and then a vector of the target variables capital Y, right. So we have to assume that this data, right, yi can be given as this f of xi, where f is the function we are approximating, plus a normally distributed error, right, and typically the normally distributed error has a mean 0 and variance sigma squared, where this sigma is an estimate of the irreducible error. There is always some data in the model which your function f of x cannot capture, right. So, that data, that error is Gaussian and it is represented by mean 0 and variance sigma square. Okay. So, now if the mean of the target variable is 0, then what you can write is then your f will be a normally distributed random variable with again mean 0 and covariance kxx, right, where x capital X is the data in the training set, right. These are the features, and as you know that in Gaussian process regression this covariance is represented by a kernel function, right. So, this kernel function, and this is something we saw in the previous lecture, also shows up in your kernel ridge regression. So, this is a kernel function. And the usual examples are the radial basis function kernel, RBF kernel, or a polynomial kernel, and so on. Now, since your y vector, right, the two values is the f vector plus the epsilon vector error, the vector of errors, your y will follow a normal distribution with mean 0, and then to the covariance kxx we have to add the irreducible error, right, and these will be added on the diagonal entries here. Okay. So, this is essentially the total error in prediction represented as a variance. Okay. Now, what can be shown, and this I will write without proof, is that the joint distribution of the training and test data can be written as follows. So, the random variables are y and f star. So, y is the training data and f star is the latent function at the test points x star. This will follow a normal distribution with mean 0 and a covariance matrix, where on the diagonal you will have kxx plus sigma squared I, and on the off diagonal entries you will have the covariance of x star and x star x. So, essentially you are applying the kernel to approximate the covariance. So, you know how these k's are computed. They are just computed in this manner here, right, through the use of the kernel function. So, the ijth entry will be the kernel function applied to xi and xj. Okay. So, this now makes it clear that this is essentially the training set values of the target variable, right. They also have some irreducible error, right, that is what we are writing here, and that is always assumed in a data oriented approach, and this f star is the latent function values at the test points. So, you can make predictions at multiple data points where the data matrix of test data is given as x star, right. and you know that kxx is the kernel between the training points and kxx star is the kernel between the kernel matrix between the training data x and the test data x star. Okay. And now you can show that the posterior probability, so the posterior probability of fx star given y, right, all the training data can be given as f star given y follows a normal distribution with mean mu star and covariance sigma star, and the mean mu star is essentially can be proved to be kernel matrix of x star x multiplied by kernel of the training points kxx plus sigma squared I inverse y vector, and the covariance is sigma star which is given as k x star x star. So, the kernel of the test points minus k x star x multiplied by k x x plus sigma squared I inverse k x x star. Okay. So, now what is the physical interpretation of this mean and the covariance? So, the mean mu star, these are the mean predictions at the test points. Okay, so, that is the prediction you will tell someone, right. So, if you want to know the data point what is the target variable at a test point, that is the value you will provide, right, to the person who is asking the question, and this sigma star, right, this appears in a normal distribution, that is the variance here. So, that represents the uncertainty in the prediction of the data points. So, this is the error estimate which a Bayesian framework provides you in terms of the predictions that you make. Okay. So, through this kernel function, right, you are checking the similarity of your test points, right, to the points in the training set, and then you are doing some sort of a weighted combination of the data in the training set, and this is what we had said is true in a non-parametric machine learning model. You make a weighted prediction of the features of unseen data points depending on how similar the features of that point are to features in the training set. So, to summarize, the prediction of a data point in GPR depends on how similar the features of this unseen point are to features of the points in the training set as quantified by the kernel function which attempts to model the covariance of the target variable. right, for various data points. Okay. So, this brings us to the end of the discussion on Gaussian process regression. As we discussed today, GPR is a Bayesian approach to machine learning, wherein we assume a certain prior distribution of the function that is being modeled in terms of a Gaussian process, and then we use the data to write a posterior distribution, and from this posterior distribution we can find out the mean prediction of the data points, and we can also provide an estimate of the uncertainty of the data points, right. I hope you learned something new today. Thank you for joining this class, and I look forward to seeing you next time.